We already know that chemicals form bonds, and we probably already know a lot about what we're going to talk about today, but we're going to hopefully dig in a little bit deeper. But it's also important for us to understand this so that we can add on to it and indeed go a little bit deeper. So when we talk about chemical bonding, we already know that atoms bond to try and get stability. You probably know about this idea of a stable octet. I need you to take that down a couple notches in your list of priorities, because that's not necessarily why they do what they do. And sometimes a stable octet is not achieved and atoms are still bonding. Sometimes they go from one thing in a stable octet to a different thing in a stable octet. So it's got to be more than just a stable octet. But there is this idea of overall lowering of the energy. Atoms are always trying to get to a point of lower energy, so they're going to dump energy any chance they can get. A stable octet is still not a terrible thing. It's still a worthwhile pattern, although again, it's not usually a driving force. This idea of an overall better, favorable, stable electron arrangement, which is a little bit like stable octet, only more complete, because now what happens if I don't get a stable octet? Can I still turn to this idea of a better arrangement of electrons? And there's a couple of different ways that we can achieve that stable octet. And then there's some middle ground, and then there's all these other things that we'll eventually get to. Okay, so they might gain electrons, they might lose electrons, they might also share electrons. And then what we're going to do next time is try and look into this middle ground. Well, are there times where it's something in between? And the answer is yes. Although I've just answered a question I'm going to pose to you at the end of all of this. So how do you know if they're going to transfer electrons, lose electrons, or if they're going to share electrons? And it comes down to a bunch of things. And for us, it's going to bring back those trends that we had a little while ago, the ionization energy, how easy it is for an atom to lose an electron or for an electron to be taken away. The electronegativity, which isn't so much an energy thing, but it does give us a tendency, a pattern. If an atom is good at attracting electrons to itself, then maybe it will. If it's not very good at attracting electrons to itself, maybe it won't. And then the lattice energy, which is not something that we're going to spend a lot of time talking about. It's actually, unfortunately, a really important thing that we're going to kind of gloss over, but it plays a large role in the formation of certain kinds of compounds. I'll talk about it when we get there. So ionic bonding is going to be between a metal and a non-metal, where metals have a low ionization energy, which means it doesn't require a lot of energy to pull an electron away, and they will also have a very low, I shouldn't say very low, but they will have a lower electronegativity. And then we can get that stable octet, if that's going to be our helpful pattern, by losing electrons. And then the non-metal, as I mentioned, it kind of has the opposite. It's going to have a higher electronegativity, and it doesn't really matter about its ionization energy, although it will also be higher because losing an electron was not really one of its possibilities. And then by gaining electrons, I can achieve a stable octet. So it seemed like a match made, like perfectly set up for it. We've already talked a little bit about this probably in nomenclature, where we have this notion that metals and non-metal compounds have this opposite charge thing going on, where the total negative charge, total positive charge. And that works with this because that nomenclature is based on the kind of bonding that they do. Okay? And then I'm just going to roll through this because it's stuff that we already know. And it's also not really related to bonding. So if I have something like a sodium and a chlorine, then sodium is going to lose one electron to chlorine because sodium is able to lose an electron more easily. And if I lose that electron, sodium's down to a stable octet. If I gain one electron and chlorine has a higher electronegativity, so it's good at gaining electrons, then I end up with this, and then that whole outer electron or outer orbit is no longer there. I've got a new valence, I've got a stable octet on the one, I've got a stable octet on the other. And then comes this next part where I have these opposite charged ions. They are attracted to each other. Now that is important because that attraction between opposite ions, that keeps going in all directions. So if I were to look at an ionic compound, they are always solid at room temperature. And if you were looking at a picture and I asked you to start to identifying the pairs, you would not be able to, because any one of those purple sodium atoms is effectively surrounded by green chlorine atoms, and the same is true for the green chlorine atoms surrounded by the purple sodium atoms. You don't know which one is which, but there is this repeating pattern of plus, negative, plus, negative, plus, negative, plus, negative. That is the crystal lattice, the structure, the pattern, and that attractive force of these opposite ions coming together, that makes up the lattice energy, which again is very important, but it's not something we're going to get into. That formation of the crystal releases energy, as I mentioned, and that's the lattice energy. But the more important thing is these are properly not called molecules, because I don't know which sodium ion goes with which chlorine ion. So we talk about a formula unit or whatever, but really the chemical formula that we come up with, remember nomenclature, reduced to lowest terms, that's where this comes from. Now, covalent bonds, as you possibly already know, are between two nonmetals, where each one has high enough ionization energy that losing electrons is going to be difficult, high enough electronegativity that they both like to attract electrons to themselves. And what that means is they end up sharing electrons, because neither one wants to give and neither one is able to completely take. Now, we'll come back to that. You might already be thinking of a question. We'll come back to that in a minute. So, if I share enough electrons so that both has a stable electron arrangement, not the same as a stable octet, but both have a stable electron arrangement, then I can start to form full compounds. So in this case, they just join together, overlap those orbits, and away they go. Now, both atoms are counting that pair, that shared pair, as belonging to them. So if you do the count, both of these have a stable octet. Now, we end up talking about molecules for this one. These are the proper place where molecules can properly be used, and where the formula is actually the atoms that are involved in the ratio that they're involved. So if you recall from nomenclature, we do not reduce these. Right? So we end up with these proper molecules. Okay? I'll leave it there for there. And then if you have a whole pile of them, dozens in this case, then each one is a separate unit, whereas with this sodium chloride, it was just this constant repeating pattern of the two. Right? There's no real pattern there. Okay, that was pretty brief because probably a lot of that stuff you already knew, but what would it look like with this in-between thing going on? Is there something in between the electron transfer and a electron sharing? And I've already kind of said that the answer is yes. That'll be next time. But then what would that look like and what would it mean? But we'll talk to you later.